So let's look at the rigid rotor model. So the rigid rotor model involves having two masses, M1, M2, connected by a massless and constant length string. You can imagine the string, of course, being the bond. The molecule is going to spin about the center of mass point. Obviously, that center of mass point's going to be closer to whichever atom is greater in mass. If both masses are the same, it'll just be the midpoint of the bond. But we get the spinning of the molecule at the center of mass point. And then you can relate the energy of the spinning to the rotational quantum number J. And so we get that the energy of the rotations is quantized about that rotational quantum number J, where J, of course, is taking on values of integral values, 0, 1, 2, etc. The energy is equal to h squared divided by 8 pi squared I, where I is the moment of inertia. And the moment of inertia is related to the same reduced mass of the bond, and then times the bond length squared. So the moment of inertia is just a fundamental relationship of the bond length and the reduced mass, the atoms that make up the bond. And so then the energy of rotations could be solved for this way. You can see that as you go from 0 to 1 to 2, then you're increasing in rotational energy. Now we can also substitute and use kind of a different notation scale to go to the inverse length scale like we did for the G of V, the vibrational energy in units of wave numbers. We have the F of J, the rotational energy in units of wave numbers, where B is the rotational constant, J times J plus 1, and then we can even move on to the non-rigid rotor model where we have the term like we had omega E x EV plus a half squared. Well, in terms of rotations, now our correction is D J squared, J plus 1 squared. So this is the distortion constant D to describe the non-rigidity of this bond. If this model is describing a real molecule, that bond is actually going to start stretching as this molecule is rotating. So we're going to see that there is a distortion that goes on with the bond that we can describe with the distortion constant. Now, let's do a couple things. Let's remember that we were dividing our energy by hc to go to the inverse length scale, so that if you imagine taking your equation for the rotational energy here and dividing that by hc, that's going to be the conversion you need to do to get over to the length scale so that your rotational constants are coming out and the distortion constants with units of inverse centimeter or some inverse length. Another thing we can do is look at the relative energy from J equals 0 to 1 to 2 to 3 and see, and let's just like look at the first term here and ignore the distortion term for now. And so that if you imagine plugging in a 0, you actually get 0. So we had a ground vibrational energy in terms of the ZPE, but we don't see that ground rotational energy being anything other than 0 for the rotation. So when you have a molecule with J equals 0, 0 rotational energy, unlike with vibrations where we had a 0-point vibrational energy, plug in a 1, so B times 1, 1 plus 1. So 1 plus 1 is 2, 2 times 1 is 1, so that's 2 times rotational constant, or 2B. Plugging in a 2 for J, 2 plus 1 is 3, 3 times 2 is 6, so that's 6B. Plugging in a 3, 3 times 1 is 4, 4 times 3 is 12. So if you notice, our rotational energy as we go up is increasing with each successive rotational energy level. So the rotational energy levels are increasing in a sort of nonlinear fashion. So then you can compare this with the vibrational energy levels, which are relatively equally spaced, at least within the harmonic approximation, and we see the harmonic approximation isn't too bad. We get a slight over approximation. So you could say the vibrational energy levels in a real molecule are approximately equally spaced. But then for the rotational energy levels, you can say that they are approximately increasing with some pattern about them. So we're going from 2 to 6 to 12. The next one's 20. So we're increasing systematically in rotational energy separation as we further increase in rotational energy. So then when we talk about degrees of freedom, we can get a sense that for molecules, they have 3 times the number of atoms of degrees of freedom to describe their position, their vibrations, and their rotations. So linear molecules need 3 degrees of freedom to describe their translation, 2 to describe their rotations, because the molecules being linear will have 2 rotational degrees of freedom. So they have 3n minus 5 degrees of vibrational modes. So HCl is, of course, a linear molecule. And so for HCl, we have 2 atoms. So we have 3n, so that's 6 total degrees of freedom, and then 5 to describe the rotations and translation. So we have 1 mode left over to describe the vibration. So we have 1 vibrational mode for a diatomic molecule. So then for nonlinear molecules, it's 3n minus 6 because we have a 3rd rotational degree of freedom. So this might be a molecule like H2O. So for H2O, you can look at this and see that we have 3 n total atoms is 9, and then minus 6 rotational degrees of freedom leaves 3 vibrational modes. So we can compare N2, 1 vibrational mode. Now IR activity, let's look at that in a moment. HCl, 1 vibrational mode. Water, 3. Now CO2 is linear, so CO2 being linear has 3n minus 5 to describe translation and rotation, so that leaves 4 behind for vibration. So CO2 has 4 vibrational modes. Now let's look at the issue of N2 being IR inactive. What has to happen for infrared light to be able to be absorbed is the infrared light has to cause the molecule to undergo a change in dipole moment. So one of the things, maybe we didn't discuss this yet, is that there has to be a change in dipole moment through the absorption of light. So the delta mu, this is the symbol for dipole moment. So there has to be some sort of transition dipole moment for the molecule to absorb infrared light. And so for a homonuclear diatomic molecule like N2, there's no way it can change its dipole moment through absorbing light, since you have the same atom. No matter what the bond length is, no matter how this molecule is vibrating, it's going to have exactly a 0 dipole moment. So it's impossible for a homonuclear diatomic molecule to absorb infrared light. But luckily for HCl, it can absorb infrared light, so it has an infrared mode, not because HCl per se has a dipole moment, but because the molecule having 2 different atoms allows the molecule to have a different dipole moment as it absorbs infrared light. So if you compare HCl with its ordinary bond length, say with a slightly longer bond length, then that causes a change in dipole moment. The dipole moment, of course, changes as the charges in the atoms have a different separation. Now, water is probably not so surprising that all of its modes are IR active, given that it's a nonlinear molecule, and it also is a molecule that has a certain polarity associated with it. And so if you change the bond lengths, you're vibrating those bonds, all the modes are going to be IR active. Now CO2, this one might be kind of confusing to some because the molecule is nonpolar, no dipole moment, but if you imagine this oxygen, say, stretching in a nonlinear fashion, if you imagine what's called the asymmetric stretch, where one of the oxygen-carbon bonds is shortening, the other one's lengthening, now that molecule is going to pick up a dipole moment and have a different dipole moment than that of CO2 of 0. So some of the modes of CO2 are IR active, allowing CO2 to absorb infrared light. Only reason we bring this up is just to kind of mention that N2, oxygen, argon are most prevalent substances in the atmosphere are inactive or unable to absorb infrared light. So they're unable to act as any kind of greenhouse gas absorbing heat in the atmosphere, whereas CO2, water, vapor, methane gas, any organic substance that gets in the air is going to be capable of absorbing infrared light. And if you think about the sort of the increasing nature of man-made compounds again in the atmosphere, those that are greenhouse gases, there's only a small percentage of the substances in the atmosphere that are capable of acting as greenhouse gases. And those are the substances primarily that we're pumping into the atmosphere without much regard, or at least previously without much regard for the effects that they may have. So just something to think about in terms of a application of this type of experiment to the real world. Now let's move on from here. So let's move on to summarize that our vibrational, or that the energy of our molecule here, we're sort of summarizing that it has an energy associated with its vibrational quantum number and its rotational quantum number. We're not concerned with the electronic state because the molecule is not undergoing a change in electronic state. but we have the vibrational energy plus the rotational energy. So it's sort of like saying if you have a molecule that you know is in some um, um, particular vibrational energy level, let's say it's in J equals 1, then the molecule is going to have whatever energy of the vibrational energy level of 0 plus whatever the rotational energy level would be to be in the J equals 1 level. So that you can think of molecules as having some vibrational energy plus some rotational energy. So then to summarize, our vibrational energy to just one of the corrections is given here, and then the distortion term correcting the rigid rotor model is shown here. And then we've also added these little symbols here to kind of show that if the rotational constant, if you recall, is related to the moment of inertia, the moment of inertia is related to the bond length of the molecule. As the bond length is changing, as we're going from V equals 0 to V equals 1 to V equals 2, that the bond is actually lengthening. If you imagine the midpoint of our curve, since the bond's approaching being broken, the bond length is increasing as we go from V equals 0 to 1 to 2. So as that bond's lengthening, you can understand that the rotational constant, the constants that are trying to describe the spacing, the rotational energy levels are going to be impacted as well. So we can sort of understand how our anharmonicity is playing a role in deviating from harmonic behavior as well as deviating from rigid behavior. So we get the break in rigidity due to the lengthening of the bond through rotations, and then the lengthening of the bonds from V equals 0 to 1 to 2, etc. And so then what this allows us to do, and something to think about throughout this experiment, is that we can maybe understand a B0 and a D0. These are describing the spacings of the rotational energy levels in the V equals 0 level. Then we have like a B1 and a D1 that are describing the spacings within the V equals 1 level. We have things like a B2 and a D2 describing the spacings of the rotational energy levels in the V equals 2 level, etc. And these are values that we're going to find that we can determine from an experimental infrared spectrum of HCl. So we're laying the ground here on day 1 for a lot of the things that we're going to be working with later in the experiment, but the idea will be get some data from an infrared spectra, solve for B0, D0, solve for B1, D1, solve for B2, D2, and then relate these back to some fundamental properties of our molecules. Okay, so let's move on. So moving on to getting us towards the activity 3 for today is going through some of the sort of equations that relate the rotational energy, moment of inertia, our rigid rotor model, the rotational constant itself. So this is an equation that we were talking about before, where you had taken the rotational energy here, dividing by hc, so you get h divided by 8 pi squared ic is rotational constant, and then I is just related to the moment of, well, I is the moment of inertia, but it's related to the reduced mass of the bond times the bond length squared. So if you know the bond length of a molecule, you can solve for that, for the moment of inertia, plug it in, and then solve for the rotational constant. So this is like a key equation we're going to use a lot in this experiment to be able to go from bond lengths with I over to solving for a rotational constant. That's what you're going to do in part of activity 3. Then later in the lab, you're going to kind of do this the other way around, where you're going to take a rotational constant that you know and use it to solve back for the bond length. So if you jump ahead to appreciating that in the lab, you're going to try to solve for B0, B1, and D1, B0, B1, and B2, and then from those be able to solve for the bond length in V equals 0, the bond length in V equals 1, and the bond length in V equals 2, and then you can compare all those bond lengths and kind of see what they're equal to from your experimental spectra. Equation 14 is getting into the non-rigid rotor model as we were discussing, and then moving on to one more set of equations before we get to the activity. So here's just showing the non-rigid anharmonic model for B and D, and then a more general expression for BV and something called BE and alpha E, and then DE and beta E. These are correction terms for trying to describe some equilibrium value for the rotational constant, relating it to this correction parameter alpha, and the same thing for the distortion constant. There's actually a second way to solve for the distortion constant, as a relationship between the rotational constant and the harmonic frequency. This is probably the more useful equation for DE that we'll use in this lab. But for activity 3, what we're doing here is we're looking up the um, equilibrium bond lengths on NIST for HF, HCl, CO. And then from those, we're solving for the moment of inertia for those molecules. And then from there, we're trying to solve for their BE values, their equilibrium rotational constants. And then the in inverse centimeters. And so the thing we're going to have is you're looking up these bond lengths. They're going to be in angstrom. Convert that to inverse meters, maybe the inverse, the bond lengths are going to be in units of meters, not inverse. So the bond lengths you're going to look up here can be in units of angstrom, and then relate that to units of meters, and from there perhaps to centimeters, so that you can then do your conversions over to inverse centimeters for the rotational constant. Okay, and so be sure to use your isotopic masses that you accurately look up as needed. And so that's essentially activity 3, is just solving for a series of rotational constants.